talks with a break in between. Then we'll have to have a longer break for lunch. I think we are already being recorded, right, Omiyad?
Yes, we're good.
Wonderful, thank you. Okay, in that case, Clara, please go ahead. The stage is yours.
Okay, thank you very much. Thank you all of you for attending live. And as was mentioned earlier, please feel free to ask questions. It's a pleasure to remember this great semester we had in Berkeley. Unfortunately, we can't meet face-to-face, but still it's nice. And I'm also having coffee in the appropriate mug, just in thinking about Berkeley. So I'm going to tell you about the Lightning Network, about its costs, about the implication of the costs. This is a joint work with Gul Huberman from Columbia University and Paolo Gussini from Dublin University. So before we, Before we jump into the details, I want to have a quick second for a meta discussion. So we all know and love Bitcoin, but we know also that it's both slow and expensive. And the Lightning Network is a secondary solution built on top and supposed to solve all of these problems and make Bitcoin more usable, more approachable, and so on. The Lightning Network is being built right now. So decisions, crucial decisions about the system are happening pretty much as we speak. And decisions that will be made now, it's going to be very difficult to change them in 2 or in 3 years. This is why I think it's very, very important to study the Lightning Network right now. And so to help make the correct decisions, taking this whole network into a direction that we see as good, positive, and so on. So let's go ahead and jump right in. Okay, so I'm going to talk about the Lightning Network, then I'm going to talk about the cost of a single channel, then the implication of this cost on the network, and finally, as much as time allows, we will do a short discussion and I'll present a few open problems that I find interesting. So first of all, channels in the Lightning Network. So the basic of the basics, I assume a lot of you know them, you know this, but just to make sure that we know where we're standing. This was introduced by Poon and Raja in 2016. And in general, in a Lightning channel, there are 2 parties. Each party commits a sum. It doesn't have to be the same. And once the sums are committed into the channel, they can pay each other by changing the balances. So as an example, let's assume that Alice and Bob open a Lightning channel and they commit 4 and 6 Bitcoin respectively. Okay, so we have Alice with 4 Bitcoin, Bob with 6. Now, for example, Alice wants to pay Bob 1 Bitcoin. The only thing they need to do is to change the balance to 3 and 7. So the important thing is that the opening of the channel is done on chain, which means we need to wait for the transaction to be approved and we need to pay the transaction fee. But once we got this started, Alice can pay Bob and Bob can pay Alice as much as the channel allows, but there's no other limits. And all of this happens in communication between them. So they don't need to inform anybody. They don't need to pay fees. Everything is happening only between them. And once, for example, Alice gives Bob 1 Bitcoin over the channel, Bob is guaranteed to have it. So we have that. So there's no limit to the number of updates Alice and Bob can do. It's done by exchanging site messages. It's a pretty cool system. We're not going to go into that, but I strongly encourage you to look into it because it's very interesting. And the important part is that at any point, Alice can decide to close the channel and take the balance that she is supposed to get. So in our picture, at any point, Alice can decide to close the channel, take the 3 Bitcoin, and then Bob will get the 7 Bitcoin. If Bob cooperates, this happens quickly. If Bob doesn't cooperate, Alice will have to wait, but still, in the end, she'll get her money. So if Bob doesn't cooperate, it's just a matter of time until this happens. And if Alice is trying to cheat Bob, for example, by claiming she never paid him and she still has the 4 Bitcoin, Bob can punish Alice by just taking all of the 10 Bitcoin to himself. Okay, so all in all, generally speaking, everybody can sleep well at night and know that no shenanigans can happen from the other side. So these are the channels that are the basic building blocks. But things become more interesting when we talk about links. So if there's a channel between Alice and Bob and the channel between Bob and Charlie, Alice doesn't need to open a new channel to pay Charlie. She can use she can use Bob, if he allows it, to transfer money from her to Charlie. Again, Bob needs to allow this. The way it's done in general, let's assume these are the channels we have in the beginning. Then Alice wants to pay Charlie a single Bitcoin. So she will transfer a single Bitcoin to Bob, and Bob will transfer a single Bitcoin to Charlie. Okay, so we see that Alice paid Charlie 1 Bitcoin, and Bob started with 10 Bitcoins and still has 10 Bitcoins. And in general, the chain can be much longer. There's no, at least theoretical limit, it could be length 4 or 5 whatsoever. Any questions up until here? If it's new to anybody? Okay, so it seems we're doing good. Yeah, so in general, these channels and the links between them gives rise to what we call the Lightning Network. Okay, so we have the basics done, and then now we can go to the main questions that we were interested in when we were thinking about the economics of the Lightning Network. So a basic question is, when should a channel be opened? What's going to be the cost of the channel if we have decided that indeed we want to open one? What are the implications of the network on the network of these costs? And what issues could the economic incentives bring to the Lightning Network in general? So we're going to go to some extent into each one of these questions. Good. So I'll quickly go over previous works. So actually, things that we're relying on, at least in the main ideas, go back to the 50s and 60s, to very classical papers by Baumol-Tobin and Miller-Orr. They, of course, had no idea what's a Lightning Network or Bitcoin or anything like that. But still, the questions they asked and answered there are relevant to the study of the Lightning Network. That network is more complex, but we can still draw a lot of inspiration from there. More recently, there are works on portfolio choices. And in 2017, we start seeing papers studying already the Lightning Network as it emerged and started to interest people. People are studying the economics, the game theory, they're doing simulations, they're studying the current state of the network, and there are many more results. And it's a growing field with interesting papers coming quite often. So let's talk specifically about our model. And for this, we first of all need to introduce the model for channels. So our assumptions are going to be the following. In a channel, there's going to be 2 nodes, node 1 and node 2. We're assuming that node 1 wants to send a single Bitcoin to node 2 with Poisson arrival time with some rate lambda 1. Similarly, the second node wants to send a Bitcoin to node 1, again with the Poisson arrival time with the rate lambda 2. Okay, and we're assuming that these 2 processes are independent. Okay, so each node decides at their own time when do they want to send. So we're assuming for now that node 1 is going to commit L1 Bitcoin to the channel, and node 2 is committing L2 Bitcoin. Okay, and this is the starting position where the channel airs. Now, when they want to pay each other, let's say the second node wants to pay the first node, so they change the balances. Then the first node wants to pay the second one, and it goes on until suddenly there's no more Bitcoin on the first node side. And if the first node wants to pay again, they have to reopen the channel. So we're assuming that when the channel is depleted, the two nodes immediately close and reopen an identical channel. And for simplicity, or for a notation that we're going to use, this is going to be the cost of the channel given lambda 1, lambda 2, and L1 and L2. Okay, questions about the model?
When you say that an identical channel is immediately open, which means with the same parameters L1 and L2.
Yes, yes. We're assuming that because their needs didn't change, they want to open the same channel that they opened before.
Thanks.
Thank you. So this...
Another question. Did you consider stuff like Lightning Loop or just refreshing the channel with on-chain payments?
So we haven't. We thought this model is rich enough in the results. It could be very, very interesting to put this into a deeper study, but there is an issue into putting money into the channel because we're going to try and optimize the size of it. And then in many cases, it's going to make sense just to close and reopen if we know this, but we haven't studied this, and I think it's a very interesting subject to study.
Okay, thanks.
So let's continue, but again, feel free. So this is the model of the channels. And now we want to talk about the cost of the channel. So one cost comes from closing and reopening the channel. This happens on chain. And we're going to denote the cost by B. And when we're going to compare this to actions on chain, we're going to assume that closing and reopening a channel is going to cost two transactions on chain. So a single transaction is going to cost us B half. And okay, so that's one thing we want to keep in mind when we're asking how much does the channel cost. Another thing to keep in mind is opportunity loss. We're going to lock some money in the channel, and this money can't be used for anything else. We can't buy a car, we can't buy S&P 500, we can't do anything with it. And this is something that we need to remember. Again, when talking about opportunity lost, we're going to keep in mind the interest rate, and we're going just to mark it by the letter R. Finally, so there is a trade-off between these two things. If we put a higher deposit, this means that we're going to close and reopen the channel rarely, but there is more money inside of the channel that we're not doing something else with it. On the other side, if we're going to put a lower deposit, we'll have to close and reopen the channel very often. So we'll have to play around with balancing these two things. Okay, so to sort of warm up and get used to it, we want to ask, should we open a channel? And to do this, we're going to prove the following lemma, and just to sort of get used to all the lambdas, b's, r, and things like that. And the lemma claims that on-chain settlements for a transaction stream with rate lambda is going to cost this. Okay, and this is not a very difficult lemma. We need to introduce the random variable xk, which counts the time until the kth transaction comes about. Okay, so the expected cost is going to be, so B half is just going to be the transaction fee for sending this transaction. And this thing here is going to be, is representing the fact that paying $5 today or $5 in a year, it doesn't cost the same. $5 in a year are much cheaper than $5 right now. And the way we're going to look at that is this e to the minus r times the time until we're actually going to pay this b half for the kth transaction, okay? And then just let's run the numbers. So first of all, we have linearity of expectation, which is always fun. So we can take the expectation in. Now, it's a bit of abuse of notation, but actually waiting for the kth transaction is the same as waiting for the first transaction k times, because everything is independent. This is a Poisson process. So we can assume that xk is just the sum of k independent x1s. So we can write it like this. And again, because everything is independent, we can take the k outside, okay? Now, the last thing we need to do is to use the moment generating function of the Poisson random variable that tells us this. And then we're just summing a geometrical summation, yeah. And we get the following number here, which of course agrees with the lemma, okay? So this is the general spirit of things. So now we can approximate how much things are going to cost on chain. And now when we're talking about should we open a channel, the question we want to ask is, okay, so how much does a channel cost? And then compare these two numbers. So good. So the cost of a lightning channel, this is the following. So the first part of the theorem has to do with unidirectional channels. In unidirectional channels, we're assuming that only the first node wants to send Bitcoin to the second node. So you'll find the transaction rate of the second node 0. And of course, the second node is not going to deposit anything into the channel because there's no reason for them to do it. And this is going to be the cost of the unidirectional channel. In the more general case, when we're thinking about a bidirectional channel, this is going to be the cost. It's not a very pleasant equation, but sometimes math is not pleasant and we just have to live with it. So that's that. And from this, we can already start asking several questions. So I won't run through the whole work. We proved things exactly showing which relations should lambda b and r hold for a channel to be opened. We can also show from these calculations the ratio between on-chain transactions and transactions on the Lightning Network and other things. But from here, I want to jump to something that's going to be relevant for the second part of the talk, which is the optimal cost. In all of these equations, we're assuming that the users put some L1 and L2 as a deposit, but a very natural thing to say is that they can think about it and try to choose some L1 and L2 that minimizes the cost. So now I want to talk about optimal channels. And here we're going to talk asymptotics, and we're going to assume that the interest rate is going to 0, which is a very common assumption. So given this, doing asymptotics around when R goes to 0, the minimal cost of a unidirectional channel is going to be what you see here, and the optimal deposit is what you see here. Similarly, for a symmetric bidirectional channel, that is when both sides want to transact at the same rate lambda, the optimal cost is going to be what you see here, and this is going to be the optimal deposit. So the one thing I wanted to take from this slide is this difference, okay? So as you see, there is a difference in order of magnitude between unidirectional and symmetric bidirectional channels. We can also use these results to give bounds on asymmetric channels. I'll talk about this more in the open question part, but we don't have full optimality results for any asymmetric channels, and we think it's going to be very interesting. But already from the bounds that we can get from this, we can say quite a few interesting things. Okay.
Can you maybe, so I have a question. So I'm trying to get a sense of the directions of growth. So as the interest rate goes to 0, kind of my opportunity cost to lock up money kind of decreases because there's no point for me to invest it anywhere because I will not get any. I mean, I could spend it, but it's a different story. So as I do that, it should get kind of less. It should get more and more of a no-brainer to open a channel because I have this disposable income that I cannot invest because it's not useful for me to do so. So how is it reflected here?
So I haven't showed the criteria for when do we want to open a channel, but most in the heart of it is for a unidirectional channel is that lambda needs to be greater than B over R. So when so for example, here you see when R goes to 0, you're going to open bigger channels, for example, and things like that. But it doesn't appear here, but it is reflected in the inequalities that have to do with when do you want to open a channel and when not.
Okay, and here there's just some different effect that is about lambda versus BNR.
So here's the different effect is between unidirectional and bidirectional channel. So intuitively speaking, in a bidirectional channel, you have things canceling out. So Alice sends 1 Bitcoin to Bob, then Bob sends 1 Bitcoin to her, and we're back at the starting position. So one way to think about it is a unidirectional channel is just a random walk starting from somewhere and then hopping until it hits a wall. In the symmetric bidirectional channel, there are 2 walls. We're starting in the beginning and we're sort of jumping back and forth. At some point, we're going to hit a wall, but it's going to take much longer. And from this, the channel is going to be much cheaper because for the same amount of money inside of the channel stays open longer and we don't need to pay fees as often.
Right, thanks. Yeah, that helps.
Anything else?
Maybe I'll jump in here. I mean, you probably know about all of these like multiple channels with one peer. You could just add a second channel that adds balance to your connection with the same peer, and basically have a rebalancing function that way. Did you look into any sort of rebalancing? Because I can think of like multiple ways that are starting to get established.
So we haven't because we wanted to keep the model as clean as possible, but I'm actually currently thinking about rebalancing and using again the formulas that you see here or the first formula, which was a bit more complicated. You can actually show how much can you save with a rebalancing channel, what are the meaning of it, and also a rebalancing channel, something that it allows you is to change the B here, because you can wait longer. In our model, once the channel closes, you need to immediately reopen one. But if you can do a transaction and wait for 24 hours until it goes into the network, you can save a lot of money there. So there's a load of interesting questions that I'm more than happy to talk about. I'm seeing you next week, but anybody else who's seeing this video, I'll have my email at the end. Okay, so thanks for your questions and to continue asking them. So we talked about the optimal channel sizes. And as I said, there's a great difference between unidirectional channels and bidirectional channels. And with this, we want to talk about the meaning of these differences for the structure of the Lightning Network. So we'll have to take a moment and give a few more some definitions for the network. So we're going to have the nodes in the networks, which are going to be V1 to Vn. There's going to be an underlying payment flow. So Vi wants to pay Vj with the rate lambda ij. This is just, I don't know, Vi buys coffee from Vj daily or something like that. And we're going to represent the Lightning Network as a graph, say G, with the same nodes. And the channel is going to be a directed weighted edge between nodes that decided to open a channel. And we're going to assume that all of the lambda ij's are either 0 or large enough for the transaction to happen on the Lightning Network. Okay, so these are just a small thing. So we didn't get to that part, but in the heart of it, if you're not transacting a lot, if you're a turtle to say, you're not going to go on the Lightning Network because it's not going to be worth your while and you're going to transact on chain. So this is an assumption we have with us. So now we want to connect this Lightning Network G to the underlying set flow of payments F. So we're going to say that the weighted directed graph G is a valid Lightning Network with respect to F if, first of all, for any pair VI, VJ that want to transact, there is a directed path from VI to VJ. They're able to do this. And so when everybody chose the paths they're going to use for the payments, the weight of the edges is going to be the sum of all of the rates that are going to pass through them, okay? Intuitively speaking, the Lightning Network is going to be a graph with that's going to allow all necessary payments, and the weights of the edges or the sizes of the channels are going to be optimized to the payments that are expected to flow through them. And we're going to denote by f of g the cost of the Lightning Network, and that's just going to be the sum over all of the channels. Okay. So if we're feeling good with all these definitions, we can start and ask ourselves, how do we expect the Lightning Network to evolve in light of the costs of the channels? So the one thing to remember about the Lightning Network, it's decentralized. Nobody is going to come from above and tell who should open a channel with whom. People are going to open channels with each other at their own discretion, making their own decisions. But if there is some money to be saved, we can assume that a small number of users can decide to change the channels between them if it's going to benefit all of them, or at least not to harm the interests of anybody there. In our work, we're considering two possible changes. The first we call mutation. So we're assuming there are 4 vertices, for example, but in general, there's a small group of vertices, with channels between them. And then they can talk to each other, think about this and say, okay, we should close all the channels we have and reopen this new structure here because it benefits everybody. Another change that we're assuming that could happen, we're calling hermetization. And this is, again, we have, say, 4 vertices doing their thing, and then a 5th vertex come in and says, okay, guys, if everybody is going to transact through me, you're going to save a lot of money. So as a business plan, V5 is going to take half, and the other savings is going to go between all of them. Okay, so it's not only is this going to be not expensive, you're actually going to save money, and all of us are going to be happy. Okay, so these are the main 2 changes that we're going to allow inside of the Lightning Network. Okay. So with these changes, we can already show that there are things that we do not expect to see in the Lightning Network. So a theorem that we show is that, 3 immutable means 3 vertices agree, 4 immutables, 4 vertices agree, etc. So in the Lightning Network, if every 3 users can talk with each other and get to some agreement, we will not see cycles of length 3 where all of the channels are bidirectional. And similarly, if every 4 users can talk to each other and make decisions that benefit everybody, we will not see cycles of length 4. So for example, let's assume these 3 channels were open and they're transacting with each other. At some point, somebody will realize that actually this is a better structure. So a better solution would be to give up the lower channel here and do all of the transactions between the two lower nodes through this node up here. Okay, and a similar solution can be found for C4. So one reason that this result is interesting is that when we decide to simulate the Lightning Network for various reasons, often we use standard models such as a small world or preferential attachment. And in all these models, where there's going to be a lot of short cycles just because of the structure. And from this perspective, these models and others are irrelevant or should be used with caution when modeling the Lightning Network. So this is something that we won't see. Another small structure that we're expecting not to see is the following. It's a directed path of length 2. Again, let's assume that these nodes, for some reason, decided to create these two channels. At some point, if the lambdas are large enough, somebody is bound to notice that actually, by asking the first node to pay to use payments through the third node, this makes the second channel bidirectional. And bidirectional channels in general are much cheaper than unidirectional channels. So the first node just doesn't care because it's all the same. And these two nodes are happy because this saves the costs of the second channel here. So, and actually I like this result because in some sense, this brings to light the idea of negative transaction fee. So actually this node here can, if this was an option, should have offered a negative transaction fee to the first node here, because by transacting through the third node, they will be saving money for the third and the second node. This result also tells us that the graph spanned by unidirectional channels is just going to be a union of bidirectional channels. And there's a lot of limits that we can, again, show that all the unidirectional graph and the bidirectional channels graph channel that we can have also has a lot of limits in this spirit. Yeah. So questions about this or the previous slide? Okay, good. So for now, we talked about local structure. We said there is no small graph, cycles of length 4, this directed path. But looking at this again, there's also a global implication coming from these small changes that users are doing. So to introduce this theorem, I need to introduce a few more definitions. So the degree of a node is just going to be the channels adjacent to it. And we're going to mark by small s and large s, the smallest and largest weight of edges adjacent to this vertex V. And what's actually going to be interesting for us is this R of G, which is going to be the maximum of this ratio over all of the vertices in the network. So given that, we can show the following theorem, that a Lightning Network G that has an average degree greater than this is not hermetic. That is, somewhere inside of this Lightning Network, there is a bunch of vertices that somebody can step in and tell them, close all the channels between you, create and do all of your transactions through me, and it's going to be worth your while. You're going to save money if you'll do that. So just to get comfortable with this maybe weird figure over here, for example, if all of the weights are the same, that is R of G is 1, this means that the average degree has to be smaller than 5.66, which is not fantastic if we're thinking about a network. And we were trying, so this is, I think, the least scientific part of our work. We're just trying to guess what this ratio R of G could be. So we opened our Visa printouts. We started comparing, like, where do we spend the most? Where do we spend the least? I think the maximum we found is a ratio of 5. We said, okay, what happens if we put in 10? And it's still not great. This still tells us that the Lightning Network has an average degree at most 12.7. If we wanted not to have this business opportunity for somebody stepping in and convincing nodes to transact through them. So this limit on the average degree gives rise to a possible business plan. We look at the Lightning Network. If we suspect the average degree is too large, we just find a subgraph of vertices that have a high minimal degree. If the average is high, this means there is a subgraph where all of the vertices have a high degree. We offer all of these vertices or nodes to channel through us. They save money, we get fees, and everybody is happy. The issue with that is that, in general, low average degree can be a threat to security, to privacy, to the stability of the network, but it doesn't have to be. And I'll talk about this a bit more in the discussion. So before we go into the discussion, any question about this limiting the degrees theorem? Okay, good. So let's have a quick discussion. So we talked about the cost of a single channel. This is a basic step to understand the Lightning Network. It gives rise to very interesting questions such as, could the Lightning Network at some point leave the Bitcoin behind because it's not interesting in the same way the dollar left the gold? So that's about the cost of a single channel. Limiting subgraphs in the Lightning Network with limited cycles of like 3 and 4, paths of length 2. There are other limits that we have. So this gives us a reason to believe that standard simulation tools are not relevant for the Lightning Network, at least in the future, and we should think about different ways to simulate the network. And we need to deeper understand structural implications. By no means have we found all of the structures that we expect not to see. So there's a lot more to study there. Furthermore, the low average degree, the reason we should worry about this is that currently there is no incentive towards expander-like structure. So a low degree doesn't have to be bad, okay? We can have very robust and stable graphs, but we need them to be expanders or something similar. And for now, there is absolutely no incentive that pushes the Lightning Network in that direction. And there is a lot of incentive to create a star-like structure, something which is very centralized. And this is important to think about. So here are some open problems. Asymmetric channels, either discovering what are the costs of the optimal channels, or at least giving some good bounds to deeper understand the network. And there's a lot of game theoretical questions. We were looking specifically at the objective of saving costs in a very specific model. We can think about alternative objectives, alternative models, and again, how do we steer them towards an equilibrium that we feel comfortable with and we're thinking is going to be healthy for the network. And another open problem that we haven't touched at all in our work is the questions of fees. What are going to be the fees in the equilibrium, and how are they going to affect the structure and in general the health of the network? So thank you for your time. Questions, comments, maybe you answered something while I was chatting.
Thank you, Clara. So are there questions? So I do have a couple, maybe while others are maybe processing. So how much of sort of this theory do we see reflected in the actual Lightning Network graph? So for example, structures that shouldn't arise, do they indeed not arise, or are they rare? Or are there like, special features of the graph that, maybe is worth trying to explain?
This is a very good question, but the Lightning Network is very young. For example, for now, you can only open unidirectional channels, at least in spirit. So you can transact both ways, but only Alice can deposit something into the channel and Bob can't when they open. So they're planning to change this. They're working on the solution. And another thing, for now, the Lightning Network is mostly hobbyists. People are doing it half for fun. Some people are doing it professionally, looking into the future, but there isn't a lot of economic perspective in there. So the MBAs are not at the Lightning Network yet. So it doesn't look like anything that we expect. But this is not surprising because we're trying to think about the Lightning Network in the future when it would be used at least on a daily basis. So for now, the Lightning Network looks, I think, pretty much like preferential attachment. But if it's going to be if it's going to be adopted, there's no way it's going to be stay that way.
Okay. Thank you. I see there's a question. Go ahead.
Yeah, I was wondering, have you compared how the simulation based on your model looks in comparison to the actual Lightning Network that has established itself?
So we haven't, and we haven't even, so we have a few do's and don'ts for simulating the Lightning Network of the future, of how do we expect it to be. But we haven't done this, and in some sense, I think it's not going to be very useful because the Lightning Network now is not the way it's going to look when it's going to be adopted and used by, general public, if you may.
I'd have more questions, but if other people have questions, I'd let them go first.
Yeah, go ahead. I mean, and also if somebody else has a question, they can raise their hand.
Okay. Yeah, Jacob.
Hi, Jacob.
Yeah, I raised my hand, sorry. Two kind of related questions. One is that it seems like the model is more general than just Lightning. Right?
Oh, yeah.
I was thinking throughout the talk of just banks doing settlement with each other, not just, and assuming there's some similar cost structure, some kind of collateral they need to hold with each other to lock down funds, your model may be interesting for the current finance world, not just Lightning Network. And the questions that people have been asking, you can ask about that. Is there one bank that serves, all of Africa, as you predict that it's going to be more efficient than a bunch of small banks?
So this is a very good question. It has to do with the papers that the classical Baumol-Tobin and Miller-O papers that we were looking at when we started this work. A big difference that you'll find between the banking system and the Lightning Network is that, for example, in the Lightning Network, you always have the option of transacting on-chain. The banking system is not a second layer above something unless you assume you're going to fly around with dollars in suitcases or something like that. Mm-hmm. So I think that the comment is very good in the sense that I think this work is relevant for other second layer solutions in other cryptocurrencies or maybe other solutions. But it's not clearly good for banks because it's the first layer and not the second.
Even if you don't have the first layer, you still have the cost structure right? Like your
Right.
formulas for the cost structures can still apply. And the second question is like the formulas that you gave like seem to rely on the random walk structure, on the randomness, on the exponential arrivals, Poisson arrivals.
Yeah.
And of course, it's a fine assumption. I was just wondering whether you thought about those expressions given other distributions, and whether we should think of like like what would happen if you had like more bulky transactions. Like suppose my transaction.
So something that we definitely, so in the model, the way I presented it, we're assuming that at any point, Alice is sending exactly 1 Bitcoin, which, but so something we're already proven that this is more general than that. So we can show that pretty much the same works if we have some kind of a random distribution with some limits on it, but we look at if the expectation is lambda, then it's going to look pretty much the same. So this is something that we looked at, but we haven't looked at things like dependencies or other maybe more sophisticated models. And always happy to talk about these things because I think this is like a basic building block, but I think there's a lot more to do on top of this.
Great.
Was there one more question or?
I had more of a comment still. There's a few enterprises that are running professional channels already, like Bitfinex and Lightning Labs, of course. And I was just wondering whether you had asked them what sort of things they optimize their channel operation for. It might be informative for building a more comprehensive model.
So I had informal discussions with them. So I don't want to speak for them, just not to say something which is not exact. But but for now there isn't, specifically at least at the user end, there isn't really a deep thought in that direction. I think it has a lot to do with the engineering and technical challenges that they're currently focused at. They're thinking about this, but I don't think there was serious work done in that direction. And I'll be happy to learn if there is.
Okay, so maybe this is a good time for taking a break. Thanks again, Clara, for the great talk. So
thank you so much. There's my email, Twitter. I'll happy to hear any of your thoughts.
So we'll resume with Elaine's talk, let's say in 10 minutes. So maybe just a few minutes past the hour. And of course, those of you who want to just stick around here and chit chat, you're welcome to do so. So see you in a few.